Hello everybody, welcome into another lesson. So today we are going to introduce the inverse trigonometric functions. So up until now we've been doing regular trigonometric functions, which the goal is to find the value of a trigonometric function of an angle. Well, inverse trig functions we're working the opposite way. We're trying to find the value of an angle. So, for example, you have f of x equals sine negative 1 of x, which is also listed as the inverse sine of x. That's how you would read that. You also will sometimes see it written as arc sine of x. These are both used interchangeably. Either notation you may see, they both mean the same thing for the inverse sine function. So, when in general we think of an inverse function, the domain of the original function becomes the range of the inverse function, and the range of the original function becomes the domain of the inverse function. Well, if we think about the original sine of x function, your range rather is from negative 1 to positive 1. That's your range. So that means the domain of the inverse sine is from negative 1 to 1. Now, what's different though is your domain of the original sine function is all real numbers. But for the inverse function, the domain is restricted from negative pi over 2 to pi over 2. Well, we know that the sine of negative pi over 2 is negative 1, sine of 0 is 0, and then the sine of positive pi over 2 is positive 1. Thus, you restrict every value of the domain that you need, and you turn it into the range in the inverse function. So why don't we go ahead and graph this? So when x is negative 1, if we take the sine inverse of negative 1, you'll be down to negative pi over 2. If we take the sine inverse of 0, you would have y equals 0. Then if you take the sine inverse of 1, you would have y equals pi over 2. So here's going to be your graph of the inverse sine function. Now, the idea of the inverse function is for the sine inverse, the sine of what angle gives me the sine of x. As opposed to finding the sine of an angle, this is asking the sine of what angle gives me a sine of x. So that's the whole idea with the inverse functions. So there's your inverse sine. Let's go on to the inverse cosine. Alright, so you list these much the same way. It'll look like cosine negative 1 of x, which is read the inverse cosine of x, or you could also say the arc cosine of x. The idea is asking the cosine of what angle gives you a cosine of x. Well, your domain is still negative 1 to 1 because those are your maximum and minimum values of the original cosine function, so that becomes your domain. However, your range is different. If you take the cosine of 0, you get 1. If you take the cosine of pi over 2, you get 0. If you take the cosine of pi, you get negative 1. So you capture that full range in that interval of the domain of cosine of x. So therefore your range of the cosine inverse is going to be from 0 to pi. So that's a little bit different with the cosine inverse. Here's pi over 2. Here's going to be pi. Actually, it just dawned on me, I might want to list this one over here. So there's your range, 0, pi over 2, and pi. Alright, so if I put in negative 1 for x, that's asking me the cosine of what angle gives me negative 1. That would be pi, right? So When x equals -1, my y value is pi. Okay. Now, if I put in x being 0, the cosine of what angle gives me 0? That'd be pi over 2. And then, if I put in +1 for x, the cosine of what angle gives me 1? That would be 0. So let's draw the curve of the cosine inverse function. And there's your curve for the cosine inverse function. So a little bit different than the sine inverse. All right. Now, let's talk about the cosecant inverse. Since they're the reciprocals of the sine and cosine, cosecant's the reciprocal of sine, so it would make sense to deal with the arc cosecant function next. So we're going to deal with the cosecant inverse of x, which means that we're going to have the this is the same thing as arc cosecant of x. This is asking the cosecant of what angle gives you a cosecant of x. So having said that, what is your domain? This changes a bit. So what's your range of the normal cosecant function? It's normally going to be from -infinity to -1. So the first part of your domain is going to be from -infinity to -1 inclusive. And then it skips from -1 to 1, then you go from 1 inclusive to infinity. So your domain of the cosecant inverse is -infinity to -1 inclusive in union with 1 inclusive to infinity. Now this is where it gets a little hairy. What's your range? So yes, the cosecant is the inverse of the sine function. And you're still going to deal with the range being from -pi/2 to pi/2. But if we look at 0, which is in between, if you take the cosecant of 0, it's undefined. So you're going to have a horizontal asymptote there. So your range is going to be from -pi/2 inclusive to 0 non-inclusive in union with 0 non-inclusive to pi/2 inclusive. So you have a little bit of a different range. It just skips 0. Now, that means you're going to have a horizontal asymptote at y = 0. So let's put -pi/2 down here. Let's put +pi/2 up here with a horizontal asymptote at y = 0. So what gives us a cosecant inverse of -1? That's definitely going to be at -pi/2, right? So when x is -1, we'll be down to y = -pi/2. But if you go to the left of it to go to -infinity, it's actually going to get infinitely closer to y = 0 without actually reaching it. And then if we put in +1 for the cosecant, what gives you a cosecant of +1? That's going to be pi/2, right? And then if you go to the right of that towards infinity, it's going to get infinitely closer and closer to 0 without actually reaching it. So you have a split graph for your cosecant inverse function. So that's definitely different. And of course now we are going to do the secant inverse. Alright, so let's take f of x equals the secant inverse of x, or otherwise known as the arcsecant of x. And this is the same as saying the secant of what angle gives us a secant of x. Well, your range of the secant function is still from negative infinity to negative 1 inclusive in union with 1 inclusive to infinity. So that becomes the domain of the secant inverse. Now we need to identify the range. Okay, well, what was the range of the normal, what was the range of the cosecant inverse, I'm sorry, of the cosine inverse, since the secant's the reciprocal of cosine? The range of the secant of the cosine inverse was 0 to pi. Well, that is in fact going to be, that will in fact then be your range. However, at pi over 2 you'll have a horizontal asymptote. So your range will be from 0 inclusive to pi over 2 non-inclusive in union with pi over 2 non-inclusive to pi inclusive. So let me graph these here. So here's going to be pi over 2. Here's going to be pi. So at pi over 2 we have a horizontal asymptote. You're going to see just how this works in just a moment. Alright, so there's 0, pi over 2, and pi for our y values. If we put in x equals negative 1, the secant of what angle gives us negative 1? That's going to be pi, isn't it? So we'll be up at pi, and then if you go to negative infinity, it's going to get infinitely closer and closer to that y equals pi over 2, but it won't actually reach it. Now, if I put in positive 1, I'll get a y value of 0. And then if I go to the right towards infinity, I'll get infinitely closer and closer to y equals pi over 2 without actually reaching it. So there's going to be my graph of the secant inverse function. And of course I should list that I have a horizontal asymptote at y equals pi over 2. That would be my horizontal asymptote. So yes, you have a very similar graph to the secant function, only it's inverted. It's flipped. I mean, the cosecant inverse function is just inverted. It's flipped. Alright, so that just leaves the inverse tangent and inverse cotangent functions, which we'll talk about. So f of x equals the inverse tangent of x, or also otherwise known as the arctangent of x. So these are both ways you would see the inverse tangent function listed. This is asking you the tangent of what angle gives you a tangent of x. So let's identify the domain. Well, okay, so what is the range of the original tangent function? Your range is actually from negative infinity to infinity, which means the domain of the inverse tangent is the set of all real numbers. Now, what about your range? This is where it gets a bit different. So, if we look at negative pi over 2, we know for the original tangent functions, you have asymptotes, vertical asymptotes at odd multiples of pi over 2, such as negative pi over 2 and positive pi over 2. Well, guess what? That's your range for the inverse tangent function. However, that negative pi over 2 and pi over 2 are both non-inclusive this time. So your range will take on every value between negative pi over 2 and pi over 2. It just won't actually reach them. So this means you're going to actually have two horizontal asymptotes. Those will be found at y equals both plus and minus pi over 2. Those are your horizontal asymptotes. So let's go ahead and do that here. Negative pi over 2, and then here's positive pi over 2. So let's draw these horizontal asymptotes. Then we have another one at positive pi over 2. All right, so let's see. Because the domain of the tangent inverse of x is all real numbers, but what if I put a negative 1? What gives me a tangent inverse? What gives me a tangent of negative 1 within this within the range? That would end up being negative pi over 4, which would be about right here. What gives me a tangent inverse of 0? That, of course, would be the 0 angle. Then what about the tangent inverse of 1? What gives me a tangent of 1? That'd be pi over 4. So here's how it's going to look. The further left of 1 you go for x, it's going to get infinitely closer to y equals negative pi over 2 without actually reaching it. Then the further right you go from x equals 1, it's going to get infinitely closer to y equals positive pi over 2 without actually reaching it. So this almost looks like the cube root of x with a graph, only it's the inverse tangent. So here's the standard graph of the inverse tangent, and then you guessed it, last but not least, we need to do the inverse cotangent. So f of x equals the cotangent inverse of x, or the arc cotangent of x. This is the same as saying the cotangent of what angle gives me a cotangent of x. Well, my domain is still all real numbers. That hasn't changed, but my range has changed. If we take alright, so if we go to 0, we have definitely a vertical at the original cotangent function. You have vertical asymptotes at integer multiples of pi, such as 0 and pi. Well, guess what? That just became your range. Your range is from 0 non-inclusive to pi non-inclusive, which means your horizontal asymptotes can be found at y equals both 0 and pi. So here's 0, that'll be a horizontal asymptote. Let's do pi. So you have another horizontal asymptote at y equals pi. Well, within the domain, within the range rather, what gives you, if you put in -1 for x, what gives you a cotangent of -1 within this range? Well, 3 pi over 4 is in the range, right? So you would actually be at 3 pi over 4 right here. Now, if you put in 0, what gives you a cotangent of 0? That's going to be pi over 2, right? Here's pi over 2. I should have probably labeled that. Here's pi over 2. And then if I put in +1 for cotangent, what gives me a cotangent of +1? That'd be pi over 4. So here's my graph of the inverse cotangent function. So the further left I go from x equals -1, I'll get infinitely closer and closer to y equals pi without actually reaching it. The further right I go from x equals 1, I'll get infinitely closer and closer to y equals 0 without actually reaching it. So the graph of the inverse cotangent function looks a lot like a reflected cube root of x shifted upward. Alright, so I think we've had enough of graphing for the day. Now, let's just do some basic evaluations of some inverse trig functions. So, let's see here. What I'm going to recommend is we draw some 30, 60, 90, and 45, 45, 90 right triangles. So here's a 30, 60, 90 right triangle. Let's also obtain a 45, 45, 90 right triangle. These are definitely going to come in handy. So let's say we were asked to find the arc sine of 1/2. So this is asking us here what angle gives us a sine of 1/2. And we got to keep in mind what the range of the arc sine is. It's from -pi over 2 to pi over 2. So if we look at our 30, 60, 90 triangle, the sine of 30 is +1/2. So your answer in degrees would be 30 degrees, or in radians would be pi over 6. So that would be your answer to the arc sine of 1/2, either 30 degrees or pi over 6 radians. Alright, let's see. How about the arc sine of 0? So this is asking us the sine of what angle gives us a sine of 0. I think that should be fairly obvious. That would be 0 degrees or 0 radians. That would be your answer to this one, 0 degrees or 0 radians. Alright. Now how about the arc cosine of 1/2? So this is asking us the cosine of what angle gives us a cosine of 1/2. If you look at your 30, 60, 90 right triangle, the cosine of 60 degrees would give you a cosine of 1/2. So your answers are going to be 60 degrees and pi over 3 radians. That would be your answer to this particular problem. 60 degrees or pi over 3 radians. Alright, now what about the arc cosine of 0? So this is asking us the cosine of what angle gives us a cosine of 0. That would be pi over 2, right? So your answer in degrees would be 90 degrees or pi over 2 radians. That would be your answer to the arc cosine of 0. All right. Arc sine of 1. What angle gives us a sine of 1? That'd be pi over 2, right? Or 90 degrees. So the answer to this would be 90 degrees or pi over 2 radians. That's exactly what we'd be looking for. All right. Now how about the arc cosine of 1? So we're looking for the arc cosine of 1. The cosine of what angle gives us a cosine of 1? That would actually be 0 degrees or 0 radians. That's exactly what we'd be looking for. 0 degrees or 0 radians. All right. The arc tangent of 1. We're looking for the arc tangent of 1, which is going to be asking you the tangent of what angle gives you a tangent of 1. If you look at your 45, 45, 90 triangle, you have it right there. So your answer is going to be 45 degrees or pi over 4 radians. That would be your answer to the arc tangent of 1. All right. The arc tangent of 0. So the arc tangent of 0 is asking us what angle gives us a tangent of 0. Well, that would definitely be 0 degrees or 0 radians, right? So you'd have 0 degrees or 0 radians. All right. The arc tangent of the square root of 3 over 3. So what angle gives us a tangent of the square root of 3 over 3? Well, if you look at your 30, 60, 90 right triangle, the tangent of 30 is 1 over the square root of 3, which is the same as the square root of 3 over 3. So the answer to this would be 30 degrees, or in radians, it would be pi over 6 radians. That's exactly what you'd be looking for. All right. Now here's a good one. The arc tangent of -1. So now all of a sudden we have the arc tangent of a negative angle. What within the domain of the arc tangent function, I should say the range, what would give you a tangent of -1? What angle would? That'd be negative pi over 4, which is the same as negative 45 degrees, or negative pi over 4 radians. That's exactly what we'd be looking for. All right, so now let's see, we're going to find the cosine inverse of negative square root of 2 over 2. So what angle gives you a cosine of the negative square root of 2 over 2? Well, if you look at your 45, 45, 90 right triangle, the cosine of 45 is 1 over the square root of 2, which is the square root of 2 over 2. But think of the range of the cosine inverse. It's from 0 to pi. Since you have a negative, you're going to have to look in the second quadrant. So take 45 away from 180, you're working with a 45-degree reference angle, you would get 135 degrees, or 3 pi over 4 radians. So that would be your answer. It would be 135 degrees, or 3 pi over 4 radians. Okay, different one. This time we're finding the inverse sine of negative square root of 2 over 2. So this is asking the sine of what angle gives us negative square root of 2 over 2. Again, look at your 45, 45, 90 right triangle. The sine of 45 is 1 over the square root of 2, which is the square root of 2 over 2. But what's the range of the inverse sine function? It's negative pi over 2 to positive pi over 2. Since your sine's negative, it's going to be in the fourth quadrant, which means you'll end up having a negative 45-degree angle, or negative pi over 4 radians. That would be your answer. Negative 45 degrees, or negative pi over 4 radians. Alright. Arctangent of the negative square root of 3. So we're taking the arctangent of the negative square root of 3. If you look at your 30, 60, 90 right triangle, we know the tangent of 60 is the square root of 3 over 1, which is just the square root of 3. But think of the range of your arctangent function. That's negative pi over 2 to pi over 2, so we're going to have to be in the fourth quadrant. So this actually means the value of this is going to be a negative 60-degree angle, or negative pi over 3 radians. That's exactly what we'd be looking for. Negative 60 degrees, or negative pi over 3 radians. And then let's see, we have the arctangent of the positive square root of 3. So what angle gives us a tangent of positive square root of 3? Well, that would be 60 degrees. So your answer would be positive 60 degrees and then positive pi over 3 radians. So 60 degrees and positive pi over 3 radians. Alright, arc cosine of negative 1/2. So what angle gives us a cosine of negative 1/2? If you look at your 30, 60, 90 right triangle, the cosine of 60 is going to be 1/2. However, your range of the arc cosine function is 0 to pi. So since you have a negative, that means you're going to be in the second quadrant. So you're working with a 60-degree reference angle. If you take that away from 180, you would get 120 degrees, or 2 pi over 3 radians. So that would be your answer. It would be 120 degrees, or 2 pi over 3 radians. Alright, let's see, the arc sine of the square root of 2 all over 2. So what angle gives us a sine of positive square root of 2 over 2? Well, if you look at your 45, 45, 90 right triangle, the sine of 45 is 1 over the square root of 2, which is the same as the square root of 2 over 2. So your answer is going to be 45 degrees, or pi over 4 radians. I think I got 2 more of these, and I got a few other problems. Alright. we got the sine inverse of the square root of 3 over 2. So what angle gives us a sine of positive square root of 3 over 2? Well, that'd be 60 degrees. You take the sine of 60, it's the square root of 3 over 2. So your answer would be 60 degrees, or otherwise known as pi over 3 radians. One more of these, then we're moving on. We're going to take the tangent inverse of the negative square root of 3 over 3. So what angle gives us the tangent of negative square root of 3 over 3? If you look at your 30, 60, 90 right triangle, we know that the tangent of 30 is 1 over the square root of 3, which is the same as the square root of 3 over 3. But think of the range of your tangent inverse. It's from negative pi over 2 to positive pi over 2, so we're actually going to be in the fourth quadrant since it's negative. This would give us an answer of negative 30 degrees, or negative pi over 6 radians. That's exactly what we'd be looking for. Negative 30 degrees, or negative pi over 6 radians. Okay. Now, sometimes doing these calculations is not quite as nice as what we've been doing. So, I only have like 6 of these. Okay, so let's take the inverse cosine of 0.75. So all of a sudden, it's not very nice. First, look at this. Can we evaluate this? What's in the parentheses? That's going to be related to your domain. What is the domain of the cosine inverse function? It's from negative 1 to positive 1, so this definitely fits the domain, meaning we can evaluate that. Now we want to get an answer in both radians and degrees. So I'm about to evaluate this here. Now in your calculators, these inverse functions will be set to the proper ranges, so you don't have to worry about that. So let's do in degrees the cosine inverse of 0.75. We're going to round to 2 decimal places. You would get approximately 41.41 degrees. Or let's see what you get for radians. In radians, you would get about 0.72 radians. So what you should get is about 41.41 degrees, or 0.72 radians. And it's very important you have it in the right mode, because as you see, you get vastly different answers. Alright, the inverse sine of 0.56. So what is the domain of the inverse sine function? That's also from negative 1 to 1. So we want to get an answer in both degrees and radians. So the inverse sine of 0.56 in degrees is going to be about 34.06 degrees. So you get about 34.06 degrees, or what do we get in radians? You get about 0.59 radians. So what you should get is about 34.06 degrees, or 0.59 radians. Alright. The arc sine of negative 0.75. Well, can we evaluate this? What's the domain of the arc sine? That's -1 to +1, so we're well within the domain. Now let's take this value in both degrees and radians, the two decimal places. You get approximately negative 48.59 degrees rather. Now let's find this in radians. In radians, you get about negative 0.85. So you get approximately negative 48.59 degrees, or negative 0.85 radians. Let's see, we're going to look for the arc cosine of negative 0.7. So yes, that negative 0.7 is within the domain of -1 to 1. So let's evaluate this in both degrees and radians. In degrees, you get approximately 134.43 degrees. So what does that give us in radians? In radians, you get about 2.35 radians. So the arc cosine of negative 0.7 is about 134.43 degrees, or about 2.35 radians. Two more of these, then I have 8 more exercises where we're going to set up some triangles. Now, good one. Arctangent of -6. So we're going to take the arctangent of -6. Well, what's the domain of the arctangent function? It's all real numbers, so we can definitely do this. So the arctangent of -6 gives us about negative 80.54 degrees. So what does that equate to in radians? In radians, that's about negative 1.41 radians. So the arctangent of -6 is about negative 80.54 degrees, or negative 1.41 radians. Last one. Then we got some triangles we're going to do. Tangent inverse of positive 5.9. So first, can we do this? In other words, what's the domain of the tangent inverse? Well, it's all real numbers, so this is definitely going to work. So let's first take degrees of the tangent inverse of 5.9. In degrees, you get about 80.38 degrees. So what does that equate to in radians? That's about 1.40 radians, or simply 1.4 radians. So you get approximately 80.38 degrees, or 1.4 radians. Alright, now for the last set of exercises, we're going to set up some triangles, and we're going to solve some things here. So these 4 are going to be easy. You have theta equals So you have x over 8. You're given a right triangle with some angle theta. Then you have x over 8. The goal is to write theta as an inverse trig function of these values. Well, how does this relate with theta? If we take the tangent of theta, you get x over 8, right? So the tangent of theta is going to equal x over 8. Well, we're going to learn in deeper detail in the next lesson that if you take the inverse of a function, you cancel out the original function and get what's inside. So if I take the tangent inverse of both sides, I'll just get theta equals the inverse tangent of x over 8. So theta is going to be equal to the inverse tangent of x over 8. And that makes sense because if you taking the tangent inverse of the tangent function is just taking the composition of a function in its inverse, which should give you what's inside, right? So that's nothing different. Alright, so we have x over 3. We have x and 3. So you have angle theta, you have side x and 3. So how do these relate? If you take the sine of theta, you would get x over 3, right? So the sine of theta equals x over 3. So how can we find theta? You have a sine, so take the inverse sine of both sides. So that means that theta is going to equal the inverse sine of x over 3. So theta would equal the inverse sine of x over 3. Two more of these, then I got 4 algebraic ones. Alright, now good one. So you have a theta, then you have a side x plus 2, and then 5. Well, how does this relate? If we take the sine of theta, you get x plus 2 over 5. So the sine of theta equals x plus 2 over 5. Then to find theta, we just take the inverse sine of both sides. So theta itself equals the inverse sine of x plus 2 all over 5. That's what angle theta would be equal to, the inverse sine of x plus 2 over 5. One more of these and we got a few algebraic ones we're going to do. The ones we've started for the past 3 we just did, and then the next 5 we do, you're going to deal with all the time in calculus, especially in Calc 2. So these are very important. Alright, let's see. You have a theta, then you have an x plus 1, and then you have a 10. So you have a theta, and then you have a side x plus 1, and then a 10. How does this relate? If you take the tangent of theta, you get x plus 1 over 10. So that would give you the tangent of theta equals x plus 1 divided by 10. So to find theta, take the inverse tangent of both sides. Theta would equal the inverse tangent of x plus 1 all over 10. So that's angle theta. It equals the inverse tangent of x plus 1 over 10. Okay. We're on the final 4 exercises. What's the goal here? So we're going to be given a right triangle. We have a theta, we have an x, and a 2. So the goal is you want to first find the length of the third side, and then what you want to do is find theta in terms of the inverse sine, cosine, and tangent functions. Actually, we could find it in all six. So let's use Pythagorean theorem to solve for the third side. We'll call this side A. So we know that a squared plus x squared equals 2 squared. That means that a squared plus x squared equals 4. So that's going to give you that a squared equals 4 minus x squared. And since we're dealing with the length, we only care about the positive square root. So a would equal the square root of 4 minus x squared. So these come up all the time in calculus, especially in Calc 2. So that means that a is going to equal, or this side is the length of 4 minus x squared. So now we need to find theta in terms of the 6 inverse trig functions. Let's start with sine. So the sine of theta is going to be opposite over hypotenuse, so that would be x over 2. What does that mean then? That theta equals the inverse sine of x over 2. And then, let's see, so the cosine of theta equals adjacent over hypotenuse, so that would be the square root of 4 minus x squared all over 2, which then means that theta would equal the inverse cosine of the square root of 4 minus x squared all over 2. And then, of course, we can deal with the tangent. So the tangent of theta equals opposite over adjacent. So that would be x all over the square root of 4 minus x squared. So that means that theta itself is going to equal the inverse tangent of x all over the square root of 4 minus x squared. Now there's the 3 original inverses, okay? Now I can teach you a quick trick for these reciprocal inverses. Let's say I wanted to find the cosecant inverse. I don't have to go through setting up my cosecant. I can make theta equal the cosecant inverse of the reciprocal of what's inside. That would be the cosecant inverse of 2 over x. If you want to find the reciprocal function inverse, all you do is set up your reciprocal function inverse and just take the reciprocal of what's inside. So if I wanted to find the secant inverse, theta equals the inverse secant, I take the reciprocal of my cosine inverse, of what's inside of that, I would get 2 over the square root of 4 minus x squared. I don't even have to go through a bunch of trouble. Or if I wanted to do it in terms of a cotangent inverse, that would be the reciprocal of what's inside the tangent inverse. That would be the square root of 4 minus x squared all over x. So if you set up your first 3, you can find the other 3 reciprocal inverse functions actually very easily. It works out quite nicely. 3 more of these, then we're done. Let me get another black marker. I sure do go through that color a lot. Alright. So, we have another triangle here. You have a theta, x, and 3. Well, we need to find the length of the third side. Again, we'll call this side A. So a squared plus that x squared equals my 3 squared if we're using Pythagorean theorem. So a squared plus x squared equals 9. So a squared equals 9 minus x squared, which would mean that a equals the positive square root of 9 minus x squared. So now I got my length of positive square root of 9 minus x squared. So let's set up our sine ratio. So the sine of theta equals opposite over hypotenuse. That'd be x over 3, which means that theta could equal the sine inverse of x over 3. That's one way to express angle theta. Let's set up our cosine of theta. So the cosine of theta equals the adjacent over hypotenuse, so the square root of 9 minus x squared over 3, which means that theta itself would equal the cosine inverse of the square root of 9 minus x squared all over 3. And then we'll do the tangent of theta equals opposite over adjacent. That would be x all over the square root of 9 minus x squared. So that means that theta equals the inverse tangent of x all over the square root of 9 minus x squared. So those are the 3 ways you can express theta with the first 3 inverse functions. We won't find the other 3 inverses this time. I just wanted to show you that trick for how to find the reciprocal inverses, the real easy trick. 2 more of these triangles, then we're done. Oh yeah, good one. So we have 2, then we have x plus 1. Alright, so we want to find the third side, we'll call that c. So this is saying 2 squared plus x plus 1 squared equals c squared. So 4 plus x squared plus 2x plus 1 equals c squared. So c squared equals x squared plus 2x plus 5, which means that side c, the hypotenuse, equals the square root of x squared plus 2x plus 5. So this one's not quite as nice. So we have the square root of x squared plus 2x plus 5 for the hypotenuse. Alright, so let's find the 3 basic inverse trig functions to represent theta. Well, the sine itself of theta is x plus 1 all over that square root of x squared plus 2x plus 5. So that means that theta itself equals the inverse sine of x plus 1 over the square root of x squared plus 2x plus 5. So there's one way to express theta. Let's set up the cotangent. So the cosine, excuse me. The cosine of theta equals 2 over the square root of x squared plus 2x plus 5, which would have to mean then that theta equals the inverse cosine of 2 all over the square root of x squared plus 2x plus 5. So there's another way to express theta. And then you have the tangent of theta would equal that x plus 1 over 2. So that just means that theta would equal the tangent inverse of x plus 1 over 2. So actually the inverse tangent one wasn't that bad. So those are 3 ways out of 6 that you can express the theta. And we got one more, then we're done. But I want to get you used to being able to do this, because when you get to Calculus 2 and you're doing trigonometric integration and having to use trig substitution to solve some of these integrals, you're going to need to know how to do this with the algebra. Okay, last one. Theta, and then you have x plus 2, then you have 3. Well, we don't know the hypotenuse, so we'll call that side C. So that means that 3 squared plus the quantity of x plus 2 squared equals C squared. So that means that C squared equals 9 plus x squared plus 4x plus 4. So C squared equals x squared plus 4x plus 13. So that means that C, the hypotenuse, equals the square root of x squared plus 4x plus 13. So that's another nasty looking one. So the hypotenuse has a length of the square root of x squared plus 4x plus 13. All right. Now let's get busy finding the three of the ways to identify the theta. So let's use the sine ratio. The sine of theta, that's going to equal x plus 2 all over that square root of x squared plus 4x plus 13. So that means that theta itself would equal the inverse sine of x plus 2 all over the square root of x squared plus 4x plus 13. That was a pretty nasty one. Now let's deal with the cosine ratio. So the cosine of theta equals 3 over the square root of x squared plus 4x plus 13. So that means that theta equals the inverse cosine of 3 all over the square root of x squared plus 4x plus 13. And then of course we got to deal with the tangent ratio. So the tangent of theta equals x plus 2 over 3, which would have to mean then that theta itself equals the inverse tangent of x plus 2 over 3. So those are 3 of the 6 ways you can express theta, and if you put any of the values in, you would find that you would get the exact same answer for theta. So that's it for this lesson. Next lesson we'll do a part 2 to inverse trig functions, where we'll talk about composition properties of inverse trig functions. Those are also very important. So I hope everyone has a great day. Take care.